All right. All right, good. Thank you very much, everybody, for joining in for our regular graduates seminar. We appreciate Dr. Correa for showing up and being willing to share her experience with us. Let me give a couple of details about Dr. Correa. She is a research scientist in the Energy Geoscience Division of the Lawrence Berkeley National Laboratory. Her research is focused on developing an intelligent seismic monitoring array for carbon capture and storage projects. She focuses on the use of fiber optics, sensing, DAS, permanent surface orbital vibrators, SOV, for developing an alternative cost-effective monitoring system. Julie is involved in the optimization of acquisition and processing flows for DAS and SOV data, as well as in the development of new fiber optic cable designs. Currently, Dr. Correa works on the Otway project in Australia as part of the CCSRMR project, and the IMS project as part of the ADM ICCS project and the Eagle Ford Shale Laboratory. Dr. Correa received her PhD in exploration geophysics from Curtin University in Australia. Her research focused on using distributed acoustic sensing for seismic imaging and monitoring applied carbon storage and storage projects. Before starting her doctorate studies, Dr. Correa worked on field geophysics with seismic acquisition processing in projects offshore Ivory Coast, Equatorial Guinea, and Egypt. Dr. Correa received her BSc in geophysics from, oh boy, Fluminense. How do I pronounce that?
Fluminense Federal University in Brazil.
Thank you so much for the save here at the end. And we appreciate you being with us. And go ahead, the floor is now yours.
Thank you very much, Michael. Thank you for the introduction. It's a pleasure for me to be here talking to you guys about seismic monitoring and fiber optic monitoring. So I've been in the lab for about 3 years now, I guess. Just after I graduated from my PhD, I started my postdoc in the lab, and now I've been a research scientist for about a year. And most of the projects that I've been working on, they are focusing, like Michael said, in fiber optic sensing for continuous monitoring using DAS and using permanent sources like the surface orbital vibrators. So for the majority of the projects I work, I'm focusing on applying DAS and permanent seismic sensing for CO2 sequestration projects. But lately, I've been also focusing and working on geothermal projects and oil and gas projects, which we'll be talking a little bit about today. So hopefully I'll be showing you how to build an on-demand permanent seismic monitoring system using DAS and permanent sources. And in my case, I work a lot with surface orbital vibrators, which is a technology that has been developed in the lab. And the use of DAS coupled with SOVs can help us build an on-demand permanent monitoring array that is specifically interesting for carbon capture storage projects, but can be applied in a variety of other applications. So just before we get started, I just want to acknowledge and thank all my contributors. All these projects and all the advancements that we have been working on and going on so far is a result of many contributions of many institutions, particularly for the Otway project. We have been collaborating for years with Curtin University, which is where I did my PhD, and they have been worked on we have been building a track for years so far on how we're developing fiber optic sensing for CO2 monitoring. Also, we have been working with Rice University with Jonathan Aho Franklin. He used to be a researcher for years in Lawrence Berkeley National Lab. And for the fiber optic sensing and surface orbital vibrator developments, Barry Fryfield, who now has his own consulting company for Class 6 solutions, we all have been collaborating for years. So everything that I'm showing here today is a result of the collaboration of multiple researchers from multiple institutions. So just to acknowledge the funding received for LBL for what I'll be showing here today is from the carbon storage program from fossil fuels, from the Department of Energy, and all the funding received for the Otway project came from CO2 CRC funding. So in this presentation, I will hopefully show you motivation for this work, and we'll go through a very brief introduction on fiber optic sensing, distributed fiber optic sensing. And I'll show you some of the results for two different projects, so in two different applications. The first one is the Otway project, which is CO2 monitoring. And the second one is the Eagle Ford Shale Laboratory in Texas, which is for hydraulic fracturing monitoring. Also, please feel free, we are a relatively small group here today. Feel free to interrupt me at any time for any questions. So seismic monitoring is usually the go-to geophysical method for tracking and imaging changes in the subsurface, especially for monitoring CO2 sequestration projects, for example, where it is crucial to make sure that the CO2 is safely stored in subsurface, and especially to make sure that they are there for decades. Usually time-lapse seismic is conducted on a regular basis. But true continuous seismic monitoring has never been fully realized due to the high costs of acquisitions and surveys and the complexity of conventional campaign-based systems. For example, the conventional technology usually uses vibro-sized trucks. They are quite large. They are not easily accessible in certain land types, and they are quite impactful on the land use. On the receiver side, it's quite common that we'll have thousands and thousands of geophones, and you need a lot of people to go and deploy the geophones and then retrieve these geophones. And now we have the data acquired, and you take months and months for data processing until you have interpretable results. So what we really want is to provide an easy, low-cost platform that's especially interesting for long-term monitoring applications. And for this, we propose the use of surface orbital vibrators and distributed acoustic sensing in conjunction. So to use fiber optic sensing and SOV, so both of these technologies used together, they are really complementary because they both allow for on-demand acquisition, they allow for continuous acquisition, and they both offer high repeatability, which is necessary for time-lapse applications. So ultimately, we can use these technologies to enable real-time data processing, for optimization and data analysis, which could lead us for fast decision making. So now, because we have both of these technologies allowing on-demand real-time data acquisition, both of these technologies can be remotely accessible. They are basically unmanned technology. So now we're able now to build a continuous flow of data processing for fast data interpretation and fast decision making. So in this presentation, I'll show you how we have been using both of these technologies. So the fiber optic sensing combined with the permanent sources to enable on-demand continuous seismic monitoring. So in this context, in the next couple of slides, I will give you a very brief overview of what distributed fiber optic sensing is, but there's a ton of reference out there if you're interested in going a bit more detail, but I will focus more on the fiber optic side because I think this is what this audience is more interested in. But if you are interested also in learning a bit more about the source side, the surface orbital vibrators, please let me know and feel free to ask any questions. But basically DAS belongs to a very specific class of sensors, which are the distributed fiber optic sensing. The distributed fiber sensors are relatively a new type of sensor in the geophysical world. their first applications were around the 70s for military use. And in the early 2000s, we start to see the first applications in geophysics, particularly in the oil and gas, for monitoring wellbore integrity and so on. So distributed fiber optic sensing basically works by using an interrogator unit. And this interrogator unit is attached to a conventional telecom fiber, and it sends a series of laser pulses along the fiber optic cable, and it constantly monitors the backscatter light. So the DAS method in particularly monitored the changes in the Rayleigh backscatter, which is by far the biggest effect governing the light backscatter. But for other methods such as the DTS, which monitors temperature, and the DSS, which monitors static strain, they are both monitoring different kinds of scattering, like the Raman and the Brillouin scattering. So the advantages of using DAS is that we can basically turn any telecom fiber into an array of seismic sensors. So basically, like I said, you have an interrogator unit connected to the fiber. As the acoustic field is hitting the fiber, the changes of the backscattered signal that this causes. So the interrogator unit is constantly monitoring the changes of the backscattered signal. And with this, it can reconstruct the acoustic field. So a few particular characteristics of the DAS when we think about comparing it to conventional geophone sensors is that the DAS is able to acquire data at a very high temporal sampling, and that can go up to 100 kilohertz, for example. This obviously is limited to the length of the fiber, but we have the possibility of acquiring really high temporal sampling. We can also acquire very high spatial sampling down to 25 centimeters, which is something very uncommon to conventional geophysical sensors. We have the ability of using fibers usually up to a couple dozen kilometers. Nowadays, we have new interrogators that have been claiming that can acquire data up to 100 kilometers by using optical amplifiers. But basically, you can acquire, you can potentially transform kilometers of fiber into seismic sensors. And when we think about this really highly sampling data, you can think that this kind of data sets generate a huge amount of flow rate, and you can easily reach terabytes of data sets with the DAS measurements. So the DAS measurement actually monitors the differences in the phase of the backscattered signal. So as the acoustic wave is hitting the fiber, it will change the length of the fiber, and with this changing the optical path between two sections of the fiber. The change in the DAS response is linearly proportional to the change in the average fiber elongation over this section of the fiber. And this reference section of the fiber is what we call gauge length, that you see a lot when we talk about DAS measurements. So there are a lot of references out there that go in a bit more detail over the nature of the DAS measurement, but this is just a very brief overview, but let me know if you're a little bit more interested. This reference in particular is from Daly, 2016, when he explains the comparison between geophones and DAS measurements. So there are many advantages of using DAS when we compare to conventional receivers, but there are also many limitations. The obvious advantages are that now, if you have a fiber optic installed in your well, you can basically have seismic data for the full well coverage, which is not common when you talk about conventional VSP data acquired with geophones. They are only usually acquired over a small interval. The data is acquired simultaneously along the fiber, also an advantage, given that for conventional VSP surveys, you have a long rig time to acquire and pull the tools along the well. The fiber itself has a long survivability, so it is really ideal for permanent installations. And like we said, we have the possibility of acquiring data at high spatial sampling, high temporal sampling, and it can be cost effective in the long term. However, we also have a lot of limitations, and usually when we talk about DAS measurements, DAS most of the time is a little bit noisier than geophone measurements or hydrophone measurements. Now, this is changing a little bit as the technology is advancing with new interrogator units and new types of engineered fibers. We can now get data quality. We can now get basically signal-to-noise ratio that it's comparable or even better than conventional sensors. But when we talk about conventional telecom fibers, usually the DAS data is a little bit noisier. DAS is acquiring data along the fiber, sensing strain changes that are happening along the fiber. So it is one component measurement. The resolution is relatable to the gauge length and the pulse length. But one thing in particular that it's interesting to point out, and that's something that we have to keep in mind when thinking about acquiring data with DAS, is that DAS has a strong angular dependence. That means that the signal, the amplitude of the signal decays as cosine square of the angle of incidence. And that we have to keep in mind when we're thinking about acquiring the data and the geometry of the surveys. So there are a number of applications that have been demonstrated when using DAS. DAS have been used and demonstrated for monitoring pipeline and intrusion monitoring, for checking wellbore integrity, cement quality. In the case of geophysical monitoring, DAS has been demonstrated a lot for vertical seismic profiling, acquisition, and we have also now recently a lot of demonstrations using DAS for passive seismic monitoring, for looking at microseismics, and frac monitoring. So in the next few slides for the rest of this presentation, I will show you basically two of these applications. So for the first portion, for the results that I'll show in the Otway project, we'll talk about DAS, VSP acquisition, and VSP imaging. And the second portion of this presentation, we'll talk about how to acquire data for hydraulic fracture monitoring and what we can do with that. So for the past few years, we have been in the Berkeley lab investing a lot on using fiber optic sensing for seismic monitoring. And in particularly, we are looking at permanent monitoring technologies and how to use SOVs and DAS in a number of applications. So in this slide here, I'm just showing you and giving you kind of an idea of the kind of projects that we have been working when we talk about permanent seismic acquisition with SOVs and DAS. So a lot of these projects that we are using SOVs and DAS for CO2 sequestration. We're also using SOVs and DAS for geothermal monitoring, unconventionals monitoring, and near surface monitoring. So these 5 projects are just kind of an overview, so you can have a look, so you can have kind of a sense of where we are applying these acquisitions of this kind of technology and for what applications. But basically the Otway, the ADM project, and the Red Trail, which is a new project to start in North Dakota, we're all using SOVs and DAS for continuous seismic monitoring of CO2 injection. So basically for having a fast assessment of tracking the CO2 in subsurface. The SFL project, which is in the Eagle Ford Shale in Texas. In this project, we're interested in looking at time-lapse changes due to fracturing of unconventional reservoirs. And we have a new project coming up next year where we will also be using DAS and SOVs for monitoring a geothermal project. So in this case, we're also looking at time-lapse changes and within the zones of stimulation and how these affect the production in the long term. So like I said, in this presentation, I'll focus on two of these examples. One is CO2 sequestration, which is Otway, and the second one is hydraulic fracturing monitoring, which is SFL project. So one of these CCS projects, carbon capture storage projects that we have been closely working on along the years and has been showing some really promising and great results is the Otway project. So the project is a pilot program to demonstrate the safe containment of small amounts of CO2 methane gas mixture. The stage 3 has the objective to monitor 15 kilotons of injected CO2 using a seismic monitoring array that is fully automated and it's fully remotely operated. So basically we have an array of wells, and in this case we have 5 wells with fiber optic installed permanently. And we are injecting the CO2 in CRC3 well at 1500 meters deep. And our aim is to monitor continuously this injection and how the CO2 is behaving in subsurface. So this is a view of the acquisition geometry. So basically we have here 5 wells which have DAS installed permanently with fiber optic casings installed behind the casing. So basically these 3 wells plus these 2 wells here have conventional telecom fiber as well as engineered fiber installed behind the casing, permanently cemented. This well here has fiber installed along the tubing. And along with these 5 wells which have fiber installed cemented behind the casing, we have 9 permanent sources around the well, positioned in a way that for every source well pair, we can create a series of 2D intersects around the well. And with these 2D intersects, we are then able to create an array and monitor through these intersects the movement of the CO2 in subsurface. So again, the objective of this experiment was to demonstrate that we can acquire seismic data continuously and autonomously, to demonstrate that we can automate the seismic processing so we can have rapid plume evaluation. So now we don't have to wait for months until we acquire the data and process the data and have seismic imagings of the plume. Now we can have quick, rapid plume evaluation. Basically, by quick, I mean every day, images of the CO2 movement. And with this as well, we're hoping to decrease the acquisition footprint with big fiber size sources and decrease the societal impact of conventional seismic acquisition. So by building, again, by combining all these 9 sources with the 5 wells, we are able to kind of substitute the 3D seismic with an array of 2D transects that will be intersecting the plume.
I have a question, a simple question. The
Sure.
black lines, are they the well trajectory?
Yeah, the black lines, the well trajectory.
So they are horizontal wells, or?
No, they are, so they are vertical wells that at a point in the bottom, they slightly incline.
Okay, so you go down sort of, you go vertically, then you go horizontally, then to the right place, then go vertically.
Yeah, yeah.
Okay.
They are all, so for 5 and 4, they are all coming from the vertical tree,
Okay,
which is injection well, and then they have a 15-degree, I think, inclination.
Okay. Thank you.
Yeah, sure. So these pictures here, just to demo, to show you guys how the installation of the SOV sources are. Like I said, I'm not going to go through too many details on the sources, but let me know if you have any questions. But we did all this installation just before the pandemic. It was March that we went to Australia, and we installed all the SOV sources for this experiment. And for each location, we have 2 sources, a larger source, which is 10-ton force, and a smaller one, which is 5-ton force. And these sources are basically generating data. Each source goes rotates, so generates a signal 3 hours a day. So it takes 2 days to go over the full 9 sources, because they can only, as an agreement with the landowners, they cannot rotate during the night. So to allow only for daytime operations, the 9 sources go generate data during one cycle is during 2 days. So both sources are rotating at the same time. And there's a near-field geophone that's acquiring the data. The data from the near-field geophone is sent to the data hub that we have just on site, as well as all the data that's acquired in all 5 wells from the DAS interrogator. It sends all the data is acquired in one central data hub, and then a seismic processing is done basically automatically every day. And by the end of the day, we have pictures of the CO2 plume. So this is an example of vertical seismic profile VSP data acquired at CRC 5 wells along the 9 SOV sources. So this is an example we have here near source to a far offset source, and by far offset we here reaching about 1 kilometer distance from the wellhead. And we computed the signal-to-noise ratio, and you can see that we get for the near offset data about close to about 100 dB signal-to-noise ratio. And as we go down to the further offset data, we get to about 50 dB signal-to-noise ratio. So you can see that we are able to look at the P direct arrival pretty strongly. We can see very clearly all the upgoing P wave reflections, converted waves PS. We have the S arrivals coming down here, reflected S. So it's quite a rich wave field. And we're very pleased with the data quality that we're getting. Also, just to mention, I mentioned that we had conventional telecom fibers, engineered fibers. This data was acquired with engineered fiber. So here we are using the Silixa Carina interrogator unit coupled with the Constellation fiber, which is their engineered fiber. So when it comes to continuous data acquisition, the large amount of data stream is a real problem So we're acquiring more than 1 terabyte of data a day. And the way that this problem is solved is that most of the data processing flow is performed on site. And the main objective is to process the data autonomously and automatically, so that by the end of the 1 SOV cycle, we have images of the CO2 plume and any other QC and data analysis that we need. So if you are interested more in the data processing side, this paper was published this year, an International Journal Greenhouse Gas Control, that describes the data processing flow and all the equipment for data acquisition on site. So this is after the injection of CO2, which happened late 2020, early this year was the end of the injection. So the early months of 2021. And on the left, you have the baseline. Over here, you have the data acquired just 1 day prior to the injection. Over here is 1 week after the injection started, which is just 580 tons of CO2 injected, where we can start to see a time-lapse signal of the CO2 coming in. After 1 month of injection, which is almost 4 tons of CO2 injected, and over here is 10 tons of CO2 injected. We see a pretty strong signal. So this tells us the DAS, acquiring VSP data with DAS, and the SOV sources are able to detect changes in the subsurface associated with CO2 injection. So this is a comparison of the migrated sections, difference sections, a comparison between the DAS SOV with the conventional data. So this cross-section here is a data extracted from the 3D survey after the injection. And this cross-section is the data extracted from after the injection from the DAS and the SOVs. So you can see that the time-lapse difference shown in the DAS and SOV matches pretty well with the conventional 3D survey. So to look at the repeatability, we compared the first break times across 1 month of operation, and this was just first thing before the injection. And in this experiment, we really wanted to understand how the DAS SOV data is repeating over time. And the way that this was computed is that we're looking at the travel time changes on the first arrival. So you can see that most of the time-lapse differences, most of these travel time changes of the P arrival falls within 500 microseconds. However, there was an event of a rain event on site, which spiked this time-lapse difference. And this tells us that the SOVs, because we're using a near-field geophone to record the signal, the source signal, it is very susceptible to changes in the near surface conditions. So this is something that we need to take into account and be careful with during data processing. So this is another example of what we're trying to achieve during the day. So this is all the cross sections. They're created, all the 2D images, they are created along the injection well, the CRC3 well. And this is the CRC3 well combined with each of the 9 sources. And here we have a 2D section that is crossing each part of the well, kind of around the well. And with this, we're able to see where the CO2 is migrating. So this is one of the QC plots that we get every day after the data processing. And we have set up the data processing flow so we get an idea of the signal-to-noise ratio changes and the repeatability changes along the day. So you can see that this is the these are just average differences, average values for each SOV well number along all vintages, so every day of the data. And with this, we get this kind of plots every day in our emails, and we can look and quickly assess if there were any changes, if there's something strange going on. And the fact that we have this high temporal sampling, which is something that's not common, having a seismic data being acquired every single day, it gives us the opportunity now to see changes that are happening at very short time interval. So changes that are happening not only at the reservoir level, but changes that are happening but at the near surface, changes they're happening, affecting the repeatability of the signal. So you can see in this plot, this is a shot gather that has been acquired. Here is every day. So now we can analyze the data at a slow time axis, right? So that's basically every single day, the same shot gather displayed side by side, and how we can see that some days the data, the repeatability changes and the signal changes with that. So that's an interesting component now, an interesting way and a different way to look at the seismic data now that we have such a high temporal sampling. So, so these were the results from the Otway project and how we were able to build an on-demand continuous seismic monitoring array to detect in quasi-real-time changes due to the injection of CO2. Now I'll show you the results from the Eagle Ford Shale Laboratory, which is another project where we have been using DAS and SOVs for continuous monitoring. So the objectives of this project are slightly different. Now the challenge is how to detect and how to track the fracture's behavior after hydraulic fracturing and treatment. And we want to understand the fracture creation and understand fracture compliance and how this affects production in the long term. However, once a fracture is created, as you guys probably know, the changes in time-lapse signal disappear fairly quickly over time. So there is a strong need here that we have measurements happening in high temporal sampling. So the inspiration for this work was actually the work from Berkeley et al. In 2018, seen here, where they acquired data just before one stage after hydraulic fracturing, and they detected a change in the time-lapse signal due to the fracture creation. He noted that this change quickly after kind of disappeared, and the change wasn't so strong because they could only acquire this data after stage 33. So, so one of the takeaways was how we could acquire data that could be sensing as the stages are going, as the rock is being fractured, and how we can monitor the data immediately after the fracturing is done. So this project, the Eagle Ford Shale project, is part of a larger effort involving different industry partners and institutions. Now I can only show you the results from a field trial that we conducted in 2019. At the moment, we are actually acquiring data continuously at a new field site location in Texas. And the hydraulic fracturing is starting in about a month. So we have been acquiring data at the moment with DAS and SOVs for about 1 month. And we will be monitoring and acquiring continuous data for the next 5 months. So throughout the hydraulic fracturing, which is starting in a month. So this is really exciting for us. But today I can only show you the results from the field work that we conducted in 2019. And the objective of this field trial was to test the use of DAS and SOVs just as a proof of concept to see if we can use them for monitoring the seismic signal along the lateral part of the well, which is the area that is going to be fractured. And in this test, we are mostly interested at looking at the signal-to-noise ratios and data repeatability, and just making sure that we could use this technology for hydraulic fracturing. So like I said, this field test was acquired in 2019, early in 2019, in Texas. And in this case, the field operator had already installed a fiber optic cable behind the casing. In this case, it was a conventional single mode fiber that was installed, so it was not an engineered fiber. And we went to the site and we installed one SOV source, close to the wellhead. So you can see here in green is the well trajectory where there's fiber. And we installed the SOV source really close to the wellhead. So this is just a few pictures of the installation. That's how the source looks like after installation. One interesting thing for this field trial is that we installed this rotary slewing bearing in the bottom of the source, and this allowed us to rotate the SOV and change the direction of the horizontal component of the source. So this generated really cool results for us. It was the first time that we did try that, so it was really just to test it out, but it was an interesting component for this field trial. This is the DAS VSP data acquired showing only the vertical portion of the well. So again, this is DAS data acquired with single mode fiber, not an engineered fiber. And you can see that the data along the vertical portion of the well shows clear P-wave reflections, upgoing reflections, clear S-wave, and converted modes. When we look at both the vertical and the lateral part of the well, you can see that the angles of incidence that I mentioned in the start of this presentation starts to play a role. And this is where it's important that we think about where to position the sources when we are looking at acquiring data on horizontal wells. So as you can see, the P arrival is quite strong. As it hits the heel, it basically disappears. And that's because the angles of incidence are basically vertical along the fiber. And the sensitivity, the angular sensitivity improves again as it goes towards the heel of the fiber. So you can see the data is a little bit noisy. Now this imagery is kind of a bit blown up, but so you can see that we can see clear P arrivals along the lateral portion of the well. This is an analysis of the signal-to-noise ratio. Again, this is the VSP data. We have here the vertical portion of the well, and here the horizontal portion of the well. Again, this we can see pretty clearly how the angular sensitivity plays a role on how the data is acquired. Here, we computed the signal-to-noise ratio for each sweep. We acquired in total 40 sweeps for this position. And we were looking at how we can improve the signal-to-noise ratio. And as a result, of course, the more you stack, the better signal-to-noise ratio you have. And this is a result of 20 sweep stacking. Also, because we are talking about time-lapse data, the data repeatability is a very important, plays a very crucial role, especially when we're talking about really small changes created by hydraulic fracturing. We need to make sure that we have enough repeatability to see that. And we analyzed all the sweeps that we acquired in that field trial, and we saw that the data, the travel time changes, the travel time repeatability falls within 500 microseconds, which relates very well with what we found in the Otway data as well, which was 500 microseconds. So after acquiring the data, we processed the data, went through the conventional VSP reflection imaging, and all these results, if you're interested, can be looked at this publication, Chang 2021. Feng Chang was a postdoc working on the FSL data, and he processed this data. So in here, he processed the P waves and the S waves, and then compared to the well tops, and the well tops correlate well with the VSP imaging. So just to summarize this presentation, I just want to say that we think that DAS combined with SOVs can allow continuous on-demand seismic acquisition. And we have seen that the data quality that we get is comparable, sometimes higher with conventional acquisitions. And we get very satisfactory levels on data repeatability as well. And with this, we think that using DAS and SOVs can be a good alternative to conventional surveys using SOV sources, especially when you're talking about long-term seismic monitoring acquisitions that need to have data acquired repeatedly with a certain frequency over a long period of time. It can be cost-effective in the long term. We were able to detect quasi-real-time changes with the small CO2 injection in Otway. And so far, the DAS and SOV equipment have been acquiring data for over a year in Otway. So we have been using the DAS and SOV equipment. It has been operational for over a year in Australia, and with little complications to date. We also saw that the DAS and SOV shows promising results detecting P wave arrivals along the lateral, and these are important. So we are able to see any changes related to hydraulic fracturing. So now we are working. Like I said, next month we'll have the hydraulic fracturing happening in December. So please stay tuned for more results coming next year on that, where we'll be using DAS and SOVs to monitor a full month of hydraulic stimulation. And there we'll also acquire not only DAS data, but DTS and DSS data continuously for 6 months. And for next year, we have a new project coming up at Forge, which is led by Jonathan Aho Franklin and Rice University. We'll also be using fiber optics data to monitor hydraulic fracturing at a geothermal site. So I listed here some of the references for both the Otway and the FSL projects if you're interested in checking it out. For now, thank you for listening, and let me know if you have any questions.
Thank you very much, Dr. Correa, for your presentation. We appreciate it. What I wanted to do was give the students an opportunity to ask questions first. Any students from our graduate, any questions from our graduate students? All right. Any questions from faculty or graduate students?
Yeah, I have a question.
Please, Dr. Mohanty.
What is the accuracy of your in the CO2 sequestration project in terms of saturation and spatial CO2 saturation distribution?
What is the what? Sorry, what is the saturation?
What is the accuracy on saturation? Suppose you get some from your interpretation some kind of saturation of CO2, right? As a distribution in space, right?
Right. Yeah, we get so at the moment the point that we are at is that we mapped the CO2 plume and we mapped the limits of the CO2 plume, but we haven't got to the point that we are estimating the CO2 saturation yet. So
what does the color represent in those maps?
Which color?
Like you have a little, like an umbrella or something, right?
Oh, I think you're talking about this one. And this is from modeling. This is from modeling the plume thickness. And this
is the plume thickness?
Yeah, that's the plume thickness, and that's just from modeling.
Yeah. And what's the accuracy here? If you measure a thickness of 10 meters, is it 10 plus minus 1 meter?
I'm not able to
okay.
Yeah, I'm not sure. I'll have to get back to you.
All right, thank you.
Yeah, no problem. But I can't point to you where for publications on the modeling.
Right. Okay.
And they might give you a bit more detail. But I mean, this plume here, probably you're looking at it, it looks very strange. That's because it's combining a previous plume from a previous stage. In the previous stage, they were injecting over here, and now they're injecting here. So it's just the combination of the two plumes.
So my real worry is, suppose this leaks through the cap rock. How much has to leak out before you would know it?
That's a great question. I don't know. We were able to, so by injecting 500 tons in the reservoir, that's when we started to see a signal from the DAS and SOV.
Okay.
Yeah. But but that's a good question. If we're able to see small amounts of CO2 leaking, especially through this fault here, that we, there might be some
Great. Thank you very much, Dr. Mohanty. Any other questions, Dr. Mohanty?
Let someone else ask.
All right, all right.
I have one other question.
All right, Dr. Torres Verdin.
Yes, thank you, Michael, and thank you. I'm going to say this, Michael, Julia Correa.
Hello, thank you.
I'm so bad. I'm so Canadian. I really have trouble with some of these names. I apologize.
Anyways, you have to roll the R's. That's.
Well, I'm Brazilian actually, so slightly different.
Correa.
Yeah.
So, you see that now you have to use the throat. Correa.
Yeah, that's right.
Okay. Anyway, so thank you so much for a great presentation. It was very nice. I have a couple of questions. What maybe in line with Professor Mohanty was asking you, what is the noise floor in PSI for the DAS? I know you showed some plots, but if I were to ask you an absolute.
What is the noise floor?
Yeah, what is the PSI? In PSIs that you can sense?
You know what? I can't. I would, for any of these questions, I would really recommend that you go to the GHT publication.
Okay.
That will give all these details on pressure and CO2 saturation and so on. I haven't been so much involved in the modeling. I have been mostly involved in the seismic monitoring and the equipment. So for any of these questions, so yeah, I would suggest to go to Jenkins.
Okay, excellent. What is the reliability of the fiber optics? I noticed that in most of the publications, I was looking for the publications actually when you were speaking, and that most of, for instance, the example that you have on screen right here, most of the fiber optics was set behind in cement, right? Behind casing and cemented. And what is the reliability of that when you do something like that? You see failures, the cable breaks.
In my experience, I would definitely choose for cemented fiber. I haven't experienced any issues with installation. Well, apart from actually from this month in the Eagle Ford Shale, when they try to install the fiber, they did run into problems that the fiber broke. So that is a real risk.
Okay.
But yeah, but in my experience, it is definitely recommended installing the fiber cemented behind the casing because the signal-to-noise ratio improvement that you get is very significant. And the kind of noise that you're getting out from installing along the tubing makes a huge difference in the data quality. Okay. So that will, I mean, if you, when you're, that depends also on the on where you make that installation. There are long-term issues that you can see in fiber, like hydrogen darkening. And the fibers have also limitations in the temperature. Usually you can't go above 150 degrees C for some of these fibers. So there are certain limitations, yeah, that need to be considered depending on where this is.
In the experiments that you were looking at, the OTE project for CO2 sequestration, have you looked at these fiber optics array in passive mode when the plume is expanding? And have you been able to harvest any information just from passive sensing?
Yeah, definitely. There's a lot of information that can come, one, from low frequency DAS, looking at the very slow strain effects. There's a lot of, it's not particularly my area of research, but there's a lot of nice publications out there showing the strain changes for low frequency DAS.
Okay.
And microseismic monitoring as well, particularly for the Otway project, which is interesting because in the beginning of historically along the CO2 sequestration, CO2 CRC, which is the facility that manages the Otway project, microseismic monitoring has not been a priority, but recently, because we now have the continuous DAS data being acquired, continuous passive DAS, we have been able to acquire earthquake that happened, regional earthquakes, but also local earthquakes that happen. More recently, there was a Melbourne earthquake that was acquired. We're able to look at very interesting nearby signals that were happening in other sites nearby the Otway project. So yeah, the passive data is quite rich.
And then last question, have you or your team looked into dispersion processing? Is that something that you can also harvest from DAS arrays?
Surface waves dispersion?
Well, this, like for instance here, I think some of the vertical seismic profiling, you're seeing a Schulte wave, right? Mm-hmm. And that's a highly dispersive mode. And I just wanted to ask you about the reliability of using fiber optics for understanding the dispersion properties of the Schulte wave here.
Yeah, we haven't really looked into that yet.
Okay, thank you, thank you.
No problem.
Thank you very much, Dr. Torres Verdin. Dr. Livsku, you have questions?
Yes, thank you very much. Great presentation. Can you hear me well?
Yeah,
We can hear you.
All right, so I have a couple of questions as well. The first one, you mentioned the geothermal well coming up. Do you know how the fiber is going to be installed for that one?
It'll be cemented behind the casing.
All right.
It hasn't been
thank you.
installed yet. Yeah.
And then following on the previous questions, you know, I'm wondering actually, all this data interpretation is great, but are you doing it manually for each job, and how long does it take? Or do you have any means to automate the process to interpret the data, you know, in a faster way?
So the folks in Cardin University, the PhD student there, has been working on the data processing, and he wrote a full process in MATLAB. So basically what it took is that you just process and get the parameters once, and then you implement those parameters in the MATLAB scripts. So there's really no effort into interpretation at the moment, and data processing at the moment, almost no effort, because it's all being done automatically on site with MATLAB scripts.
So the MATLAB is actually acquiring the data, right? But then it's the data noise, is the data resolution, you know, all other things that were mentioned before. And I'm wondering, actually, depending on, you know, different pressures and different noise levels, if that's automated into data interpretation, or somebody has to actually take the data and then manually understand the noise and, you know, the resolution and all the well conditions to interpret the data.
Yeah, so that's a good question. I mean, you can automate the parameters based on what you look at once. We monitor throughout a series of QC plots on how the noise levels are changing every day, but there's only so much that you can put into an automated data processing flow, right? So what we can monitor is what we see from the NRMS plots and signal-to-noise ratio plots that we're looking at every day. But the parameters, we can't really, you know, adjust the parameters based on noise levels. But I mean, it's fairly, you know, it's a fairly quiet area. It's kind of it's a farm area, so the noise is fairly predictable. So this hasn't been really an issue so far.
All right, thanks. And then the third question. So yes, if the fiber is cemented into a well, how do you know exactly the location of the fiber and if it's straight or not? Are you compensated for the well location, exact well location in the well? I mean, on each part of the cement is right, north, south, whatever. And if the fiber is not straight when it's cemented.
What you can do is, so first, when you acquire the DAS data, usually you do a tap test, right, to look at the start of the well. The fiber is looped in the well, so you have the end of the fiber as well. So that's a good way to look at where the start of the well and where the start of the well and the fiber is, and where the end of the well and the fiber is. It's a good way to locate it. So one way that sometimes I do is to compare with well tops and compare with gamma ray and compare with even geophone data if you have acquired at the same time, just to make sure that the depth assignment is correct.
Excellent. How long it takes you actually to compare all the data you mentioned to make sure that, you know, the fiber is where you think it is?
It doesn't take long. It depends. I mean, every time you acquire a DAS data, it's a good practice to acquire a tap test. That's just, you know, tapping on the fiber optic cable itself and then doing some data analysis. It's not, I mean, it's just a normal part of the processing. Yeah.
All right. All right. Thank you very much.
No problem.
Thank you very much, Dr. Lipsky. Thank you very much, Dr. Correa, for even staying extra time with us to answer all of our questions. We appreciate you joining us to share your knowledge and experience in this important topic, and wish you well appreciation.
Yeah, thank you very much. Thanks again for the invitation. And if you have any questions, just contact me. I have my email over here if anyone has any more questions.
Awesome. Thank you very much.
No problem. Thank you.